Okay, welcome again in this lecture, and in this we are going to construct the AVL tree. So far we have understood that how the insertion and deletion to be done in any AVL tree. So just to refresh that, insertion we are doing is the rule of BST, one is such tree, and after insertion we have to check the balancing factor of each node, and if the balancing factor is not maintaining the one value, then we have to do the rotations. In the insertion, we have four possibilities, that is called LL case, LR case, RR case, and RL case. Okay, so let us insert these nodes one by one, and then we will do also deletion in the same tree. So let's start. So we insert 12. So because initially the tree is empty, so 12 will be just inserted. Every time when you insert, we have to find out the balancing factor. So here the balancing factor is 0 here. Then we insert 19, so 19 will be inserted here, and because of this insertion, this changed the balancing factor here. So here we are using R minus L, so this is going to change from 0 to, because R is 1 and left is 0, so we have here 1. Then we insert 17. 17 we have to start from the root. This is 17 is more than 12, go to 19, 19, and 17 is less than 19, so we insert 17 here. Now because of this insertion, we need to check what is the impact on the balancing factor. So this become 0, and this will be when I do R minus L, so this becomes minus 1. And if you look at this, this becomes 2. Now here we can see that this is not balanced, so we need to do rotations. And if you look at this, this is right left. So whenever we have a right left case, we need to do right rotation at this node. We call it Y node, and then we do the left rotation at this node. So when we do the right rotation here, what you will get? You will get this structure: 12, 17, and 19 will go down. And then you have to do left rotation at this node. So what you get? You get 17, 12, 19. Now this is balanced, so you can get 0, 0, 0. Now we have to insert 6, so 6 is going to be inserted here, and because of this insertion, what we get, this will be 0, this will be minus 1, this will be 0, this will be 2 minus 1 is, we are doing R minus L, so R is 1, L is 2, so 1 minus 2 is minus 1. So again this is balanced. Let us clean this part. Now to insert, we have to insert 16, 6 we have inserted, now 18. So we start from here, 17, then 19, then 18 will be here. So the impact of this is 0. Now if you look at this, so 0 minus 1 is minus 1, and if you look here, this is 2 minus 2 is 0. This will be 0 minus 1 is minus 1, so this is again balanced. Then we insert 13. So when you insert 13, so 13 is going to be inserted here. So let me draw the figure here. 17, this is the tree that we are having. 6 and 19, 18. When you insert 13, 13 will be here. So let us look at the balancing factor. This is 0, 0, 0, 0. This is 2, and this is 2. 2 minus 2 is 0. And look here, this is 0 minus 1 is minus 1. So again it is balanced. Then 25. So 25 we will insert. So 17, 19 and 25 will be here. So the impact of this is, this will be 0, this will be 0 and this will be remain 0. Okay, then 36. So 36 will be, we'll go to right side and then go to right side and then go to right side. 36 will be inserted here, and the impact of this is, this becomes 0, then 1 minus 0 is 1 and 2 minus 1 is 1, and if you look at this, 3 minus 2 is 1 and rest will be same. So this is, again you can see it's a balance because none of the node balancing factor is more than 1. Then 80. Now when you insert 80, so again we will start from 17. This is more than 80, more than 17, go here. 80 is more than 19, go here. More than 25, more than 20, 36, 80 will be inserted here. Now if we look at this structure, what is going to happen, we'll see. Let us clean this part. So with this insertion, so we'll get 0 here, and let us change these values. So what is going to happen here, this is 1 minus 0 is 1 minus 0 is 1, then 2 minus 0 is 2. This is what, 3 minus 1 is 2, and 1 2 3 4, 4 minus 2 is 2. Now we need to find out which one is a critical node. So already we have discussed that we need to see which is our new node is a new node. From here we have to move upward and we need to find out the first node which is unbalanced. So we'll go here and we find this node is unbalanced, so we are calling this as a critical node. So this becomes your Z, this becomes your Y, this becomes your X, and this you can see this is actually R case. This is your right child of Z, this is the right child of Z, and in this case you need to do the left rotation at the Z. So when you do the left rotation, what is going to happen, this is going to go up. So what actually is we are getting something like this: 17, 12, 6, 13, 19, 18, and now because of this rotation, this 36 becomes move up, 25 goes down, so 36, 25 and 80. And let's see what is the impact of this rotation. So this is 0, 0, this is 0, this is 2 minus 1 is 1, 3 minus 2 is 1, this is 0, 0 and 0. So here you can see after the rotation our tree get balanced. So we have inserted all the nodes, and similarly you can just add some more nodes from your side to do more practice. Now let us see what will happen if we delete. So again we will delete the nodes in the same tree. So let us clean this part. Okay, so this is our tree which is balanced. Now I am going to delete 17. Now 17 is our root node. We will follow the principle of BST deletion. So whenever you have a node to be deleted having a left and right subchild, having a right and left child, then we have two options to proceed. Either you can take the in order uh, predecessor or the in order successor. So if you are going to replace this value in the in order successor, then you have to choose the smallest value from the right subtree. Or if you are going to take the in order predecessor, then you have to take the maximum value from the left subtree. So I am going to take the maximum value from the left subtree. This you have to define while writing the algorithm for your program, that which approach you have to follow. We have two options, you can go with any options. So this is having a two left and right child, so we have to find out the maximum value in the left subtree. This is the maximum value. So what is required, we need to replace this value with 17, and then we will delete this node and then we delete this node. This is what we were already discussed and studied in the BST. So our final tree will be looking like this. So 13, 12, 6, 19, 18, 36, 25, and 80. And our 17 is deleted. Now you can see here 17 is no more existing, and still it maintains the BST property. The left child is less than the root, and the right child is more than the root. Okay, but what is the impact of the deletion? Let us look. This is 0, 0, 0. This is again 0, and if you look at this is now in the deletion what we have discussed. So I will follow as per the discussion. So we have used L minus R while we are deleting, means the height of the left subtree minus the height of the right subtree. So this is 1 and this is 2. So 1 minus 2 is minus 1, and if you look here, this is 0, this is 1 minus 0 is 1, and then if you look here, this 2 minus 3, this is minus 1. So still our uh, tree is balanced because the balancing factor of each node is maximum minus 1 difference, maximum 1 difference you can say. Okay, so with the 17 there is no violation in the balancing nature of the tree. So let us move forward. Now the next to delete is 6. Now 6, we start from here. This is this 6? No. Is this 6 is less than 13? Okay, we go to left subtree. This is 6? No. 6 is less than this. Okay, we'll go here and we find the node with the value 6. Now whenever you want to delete a node which is a leaf, you simply delete it. There is no need to move any node upward or make any changes. But with this deletion, deletion is very simple because it's a leaf. But because of the deletion, their value of the balancing factor may change. So let us see what will happen. So now this is no more existing. This is our tree. So what you get, this value will be 0, and this is 1, 1, 2, 3. So 1 minus 3 is minus 2, and this will be 0, 0, 0. This will be 0. This will be 1 minus 2 is minus 1. So here you can see that already we have reached to the scenario where we get a node with unbalanced balancing factor. This is unbalanced. This is minus 2. So here we have seen that the node is deleted in the left subtree of the critical node. The node which is unbalanced is said to be critical, and we have deleted from the left subtree. So that means this is the case of L rotation. And then we have to look to the right part, and the right part, this is a root node. This is minus 1. So this is L minus 1 case. So you need to recall what is required in the L minus 1 case. So I'll show you what is L minus 1 case. This is L minus 1 case. In the L minus 1 case, you need to do similarly as we did in the RR case. Okay, so just go to our numerical. So we have to treat this as a RR case. So L minus 1 being required to do the rotations as per the RR case. So in the RR case, we are doing the left rotation at Z. So this is our Z node. We have to do the left rotation here. So when we do the left rotation here, what will happen? This will become the root node. This become the left child of this, and this become the right child of this node. So what you will observe here? You will observe this thing. 19, 13, 12. The left child of this become the right child of this, and things remain the same. 36, 25 and 80. So what is the observation? You can see here our node 6 is deleted, and we are left with this structure. So this is 0 0 0 0 0 0 and 0, and our tree is again fixed. Okay, so next move to the 18. Now again we will start from the top and we reach to this node. This is a leaf, so we delete this node directly. But because of the deletion, there may be a change in the balancing factor. So let us see what will happen. So if you delete this node, what will happen? This will be no more existing. This will remain 0, but this is 1 minus 0 is 1, and it will be not giving any impact on this because already the height remains the same. It was also 2, now also 2, so this will remain the same, and this is no more affected. So again, with the deletion of 18, nothing is going to means change in terms of the balancing factor. So with 18, we notice that there is tree is still balanced. There is no impact on the unbalancing factor. All balancing factors are in the range of difference of plus 1. Okay, so move to 12. Now when you delete 12, so 12 is again a leaf. It can be deleted directly. There is no need to make any substitution or movement of the nodes. But because of the deletion, again we need to check what is the impact of the deletion. So let us again recalculate the balancing factor here. So let me clean this area. So now this becomes 0, and if you look at this, this is 1 and 2. 1 minus 2 is minus 1, and this will remain 0 0. So again, with the deletion of 12, there is no impact or it will not going to create the tree unbalanced. So this is how we can insert these nodes and also delete, and we have seen that how the rotation can be done if the tree becomes unbalanced. So this is all for this lecture, and you can extend the tree by writing some more values for your practice so that you can able to have a good understanding of these operations of insertion and deletion, and also you will be able to memorize these cases because you need to remember these cases while you will be doing deletion and insertions. So this is all for this lecture, and I believe that you have understood the operations and the AVL trees, how to perform the insertion and deletion, and how to handle these unbalanced scenarios. That's all for this lecture. Thank you very much.